Effect of a dynamic loaded warm-up on vertical jump performance. Abstract. Human Performance Laboratory, Department of Kinesiology, California State University, Fullerton, California. Effect of a dynamic loaded warm-up on vertical jump performance. Journal of Strength and Conditioning Research, 24/7, 1751 through 1754, 2010. Considering the importance of vertical jump in several sports, an optimal warm-up protocol may help athletes perform at their maximum level. The purpose of this study was to investigate the potential effects of the different levels of external resistance weighted vest during box jumps on vertical jump performance. 20 resistance trained aged men, age 22.45 plus or minus 1.753 years, height 176.83 plus or minus 6.67 centimeters, mass 76.98 plus or minus 8.56 kilograms, participated in this study. Subjects performed 3 vertical jumps, with the greatest height being recorded. On day 1, each subject performed a control condition with no external resistance to establish a baseline vertical jump height. On the following days, they performed 4 random jump conditions with a weighted vest equivalent to 5, 10, 15, or 20% of their body weight, then rested for 2 minutes before performing 3 post-test vertical jumps. Results demonstrated no significant interaction of condition by time of vertical jump height. However, there was a significant main effect of time. P is less than 0.05, with post-test jump height 22.99 plus or minus 3.35 inches being greater in pre-test jump height 22.69 plus or minus 3.37 inches. Performing an active dynamic warm-up with or without a weighted vest produced significantly greater post-test vertical jump performance. A dynamic warm-up may improve vertical jump performance, albeit to a very small increment. Introduction. Vertical jumping is one of the important aspects of multiple sports such as basketball, volleyball, and football. If jump height could be increased because of a specific warm-up, this could benefit an athlete's performance in a multitude of sports. Dynamic warm-up has been demonstrated to garner positive results on subsequent vertical jump performances. A specific dynamic warm-up can be described as a warm-up that addresses key muscle groups and the necessary neuromuscular conditioning needed to perform a specific action, such as vertical jump. In addition, studies have also shown that a possible post-activation potentiation (PAP) effect when a specific dynamic warm-up was coupled with resistance. Past studies investigating PAP induced by heavy resistance and subsequent effects on higher power activities such as jumping, sprinting revealed enhanced performance. Previous studies have employed various types of external loading such as dumbbells, weighted vest, or barbells coupled with a movement similar to jumping or an active dynamic warm-up and produced significant performance improvements. These studies show that regardless of the type used, the concept of external loaded coupled with dynamic movements have been potential to produce significant performance improvements on subsequent power exercises. A possible explanation for the performance improvement after the aforementioned activities may be PAP, post-activation potentiation, typically occur when performing a contraction at near maximum or maximum intensity. Although the exact mechanisms of PAP are not fully understood, it has been generally proposed and accepted that PAP is associated with phosphorylation of myosin regulatory light chains, increased recruitment of higher order motor units, and a possible change in pennation angle. Based upon these concepts, if PAP can be induced, subsequent explosive activity could be potentially enhanced as well as performance or the training stimulus of that activity. Burkett et al. Used an external load equivalent to only 10% of the participant's body weight, and yet still elicited a significant improvement in subsequent vertical jump performance. This leads to the question of whether a greater or lesser load, i.e. percentage of body weight, might be elicit different responses. Therefore, the purpose of this study was to investigate the effects of different increments of load coupled with a specific dynamic warm-up and the subsequent effects on vertical jump performance of college-aged athletic men. Methods. Experimental approach to the problem. To investigate the effects of different percentages of external load on vertical jump performance, we used a within-subject design consisting of 5 testing sessions. The first test session involved establishing a baseline vertical jump score that retest fashion without any external load control. The experimental conditions required the subjects to perform box jumps using an external load weight vest equivalent to 5, 10, 15, and 20% of their respective body weight. This is done in an attempt to elicit PAP and increase performance by subsequently unloading vertical jumps. Subjects. Participants for this study consisted of 20 college college-age resistance-trained men, age 22.45 plus or minus 1.73, height 176.83 centimeters plus or minus 6.67, mass 76.98 kilograms plus or minus 8.56, having at least 1 year of resistance training experience. Participants who suffered from a previous or current injury that could inhibit influence their vertical jump performance were excluded from the study. Each participant read and signed an informed consent form approved by the university IRB before their participation. Procedures. All participants were instructed to refrain from any and all strenuous lower body activities before and during the testing period. Participants were also instructed to wear the same pair of shoes for each training condition in addition to comfortable athletic apparel. Participants were also instructed to consume water before testing. Participants were also instructed to maintain consistent eating, sleeping, and activity habits. During the first testing session, each participant's height, weight, standing, reach, and knee height were measured. Knee height was measured by taking the distance from the subject's lateral femoral conda on their right leg to the floor. The purpose of this measurement was to establish box height for each subject that would be used during their testing and exercise sessions. This was done to ensure that the intensity of the box jumps was standardized relative to each individual. During each testing session, subjects performed a 5-minute warm-up on a cycloergometer at a self-selected RPM level of 25 watts. Based on previous studies, various stretching protocols were excluded from this testing process because of the inhibitory response and subsequent degradation of vertical jump performance. On completion of the warm-up, each subject performed 3 counter-movement jumps with arm swings as high as possible and displaced veins on the vertex. On completion of a warm-up, each subject performed 3 counter-movement jumps with arm swings as high as possible and displaced veins of the vertex. Hilliard, Ohio, USA. The vertex is considered an appropriate tool for measuring jump height. The rest time between vertical jumps ranged from 10 to 15 seconds, as previous studies have observed no significant decrease in jumping performance during the indicated resting time frame. The subject's vertical jump score was determined at the difference between their reach height and their maximum jump height. The highest jump score was used as a pretest BJ score. On completion of the 3 pretest vertical jumps, subjects then performed 5 box jumps at their predetermined box height. Subjects stood approximately 6 inches in the box and were instructed to jump on top of the box. Participants were allowed to squat to a self-selected knee depth. They were then instructed to step down and wait 10 seconds. The tester then gave the subject a verbal countdown before performing their next box jump. Upon completion of the 5 box jumps, subjects retested 2 minutes in a standing position. Upon conclusion of the rest period, subjects performed 3 post-test counter-movement vertical jumps and arm swings in the same fashion as a pretest, with the highest score being recorded. For the remaining test sessions, participants were randomly assigned to 1 of 4 test conditions, performing a different test condition each session. All subsequent testing was done at the same time of day. The 4 test conditions consisted of different increments of external resistance using a weighted vest. The different increments were represented as percentages, 5, 10, 15, and 20% of each subject's respective body weight. The testing procedure for the remaining protocols were performed exactly the same as the first session, with the sole difference being the amount of resistance used during the box jumps. The rest periods between testing sessions range from 1 to 5 days. Statistical analysis. A 5 times 2 condition times repeated measured analysis of variance was performed to determine differences in vertical jump height across conditions, as a priori alpha of 0.05 was used to determine significance. Retest reliability was measured via the interclass correlation coefficient (ICC) statistic. Results. There were no significant interactions between the condition and the time, nor were there a main effect for test conditions. However, there was a significant main effect for time, p equals 0.08. Mean post-test vertical jump height, 22.99 plus or minus 3.35 inches, was significantly greater than the mean pretest vertical jump height, 22.69 plus or minus 3.37 inches, table 1. Effective size was very small at 0.09. Retest reliability was measured via ICC and resulted in 0.97. Discussion. The purpose of the study was to investigate the effect of different increments of load during dynamically specific box jump warm-up on vertical jump performance. The primary finding of the study was the post-test Vertical jump height increased regardless of the warm-up condition. Therefore, the addition of a weighted vest had no additional effect on post-test jump height compared to simply performing 5 box jumps at normal body weight. Burkett et al. Found that vertical jump performance significantly improved after box jump using resistance equivalent to 10% body weight. However, the Burkett et al. Studied two significant ways from our study. Their box height was fixed at 25 inches, regardless of the subject's height, whereas our study adjusted the box height individually for each subject according to their measured knee height. Excuse me. Our subject population, one more. Our subject population had an average lateral femoral condyle height of 20.47 inches, ranging between 19.5 and 23 inches. This meant that the highest box height any subject used in our study was 23 inches. Taking this into consideration, a box jump height of 25 inches for our subject population would have been more intense, especially during the heavier load conditions, and may have elicited post-activation response similar to Burkett. However, it's equating intensity across all subjects. However, the lower box height used in the study may have reduced the PAP effect because of the reduced intensity level. In addition, Burkett et al. Only used one level external load, 10% of body weight. In this study, because of the finding of a significant improvement in vertical jump height performance, the original hypothesis of the study was to different external loads might possibly elicit different outcomes in vertical jump performance. For this reason, test conditions of 5, 10, 15, and 20% were included. Burkett et al.'s explanation for their findings stated that through performance of box jumps, subjects became more neurologically prepared to perform a similar movement, that is, counter-movement vertical jumps. In addition, they also stated the inclusion of external load provided enough resistance to garner a muscular overload effect, therefore resulting in greater recruitment of motor neuron units. Although statistical analysis of the current study revealed no significant difference in vertical jump performance between the test conditions, there was significant improvement from pre-test to post-test regardless of the condition. It may have concluded in our study similar to Burkett et al.'s, that box jumps enhance subjects' neurological regardless of the amount of external load, thus leading to a significant improvement. In another study, Thompson et al. Found that when subjects performed a dynamic active warm-up with a weighted vest, equivalent to 10% of the body weight, and significantly increased their subsequent vertical jump performance. However, the duration of the dynamic active warm-up was 10 minutes. This is much greater in length compared to our study, in which participants spent less than 2 minutes performing the dynamic warm-up. Furthermore, subjects in the Thompson et al. Study wore the weighted vest during the last 4 movements of the dynamic warm-up while performing high explosive movements. The prolonged time period their subjects experienced, in addition to the explosive nature of the movements under load, could have potentially elicited greater PAP effects for the involved muscles. The primary finding of the study was a significant improvement in vertical jump height from the pre-test to post-test regardless of the load condition. However, given the small effect size and the absolute change of approximately a quarter inch, the practicality of the warm-up is small at best. Similarly, Thompson et al. Found that subjects significantly improved their vertical jump height after performance in active and dynamic warm-up without the weighted vest. Albeit not as great as the weighted vest condition, they stated that performance dynamic movements with a weighted vest gathered greater force production because of the enhanced neuromuscular excitation, or PAP. It may have been suggested, based on our findings in conjunction with those of Thompson et al., that performing an active dynamic warm-up without any external load may potentially still elicit significant improvements in subsequent vertical jump performance. Future research should investigate the effect of different box heights, external loads, and volume on post-vertical jump performance. In addition, because of this was a non-training study, a similar study conducted for a prolonged period of time might also be investigated, as past studies have shown performance gains in plyometric activities when compared to a short training program to a longer training regime. Practical applications. It appears that performing a dynamic box jump warm-up with a few as 5 repetitions onto a box of knee height or with or without external load may increase subsequent counter movement vertical jump performance after a 2-minute rest. Although not significantly different from the other conditions, the unloaded warm-up protocol elicited the greatest absolute improvement in counter movement vertical jump performance. Therefore, loaded warm-up jumps might be replaced with unloaded jumps with a greater box height.